Experience the power and intensity of a melt shop in action. This video takes you inside the heart of the operation, where the sound and vibration of the machines leave a lasting impression. Witness the arc furnace in action, with its powerful sparks, light show and fiery spectacle. The immense scale of the building and the sheer power of the machinery create an awe-inspiring atmosphere. Every day, the energy and force of the melt shop continue to impress, showcasing the raw strength of industrial manufacturing. Shenyang Geitai Hydropower Equipment specializes in hydropower turbine manufacturing with over 20 years of experience. Known for core technology and high-quality products like Francis and Alden turbine runners, it leads in 100% CNC machined monoblock forgings. ISO-certified Geitai operates globally, promoting green energy innovation. The manufacturing process involving CNC lathes with live tooling, twin spindle, dual turret, and horizontal boring mills (HBM) is a highly precise and efficient method used for complex machining tasks. It begins with the design and programming phase, where a 3D model of the part is created using CAD software, outlining all the necessary dimensions and specifications. This model is then converted into G-code through CAM software, which directs the CNC machines during machining. During the machine setup, tools are carefully installed on the CNC lathe, and the parameters are adjusted for the specific material and operation. The workpiece is securely mounted on the machine to ensure stability. In the machining phase, the twin spindle CNC lathe performs rough turning to remove large amounts of material, and the live tooling feature enables simultaneous operations such as milling, grooving, and threading, improving efficiency. Precision face turning and threading are also conducted. The HBM machine takes over by drilling exact holes, performing milling, and creating flat surfaces or cavities to tight tolerances. After machining, the part undergoes strict inspection using high-precision measuring instruments to confirm that it meets the required specifications. The final step involves finishing processes like polishing and applying protective coatings if needed, ensuring the product meets both functional and aesthetic requirements. The production process of the GSP drive shaft involves several key steps, each with precise specifications. First, high-quality alloy steel, such as C45 or 20 CRM-NTI, is selected. The material undergoes cutting to lengths ranging from 1,000 mm to 1,500 mm, followed by CNC machining with a tolerance of plus or minus 0.05 mm to shape components like grooves and holes. Surface grinding is performed to achieve a smooth finish with a roughness of raw, less than 0.8 micrometers. The steel is then heat-treated by heating to 850 to 900 degrees Celsius and quenching in oil or water, reaching a hardness of at least 58 HRC. Nitrogen hardening is done at 500 to 550 degrees Celsius for 10 to 12 hours to improve fatigue strength. The parts are assembled with a concentricity tolerance of is less than or equal to 0.05 millimeters. Finally, dynamic balancing is performed at 3000 RPM with a deviation of no more than 0.2 millimeters. Each drive shaft undergoes rigorous quality checks before being packaged and shipped. Goring's RF100N mills are designed for high-speed machining, ensuring optimal material removal and precision. The production process starts with selecting high-quality carbide materials, which undergo precision grinding to form sharp cutting edges. Advanced coatings, such as TLN, are applied to enhance wear resistance and heat dissipation. During operation, the RF100 speed end mills, featuring a 48 degrees helix angle and unequal flute spacing, provides smooth and stable cutting. The RF100 diver is versatile, capable of drilling, ramping, and finishing, with an internal cooling system to optimize chip evacuation. The RF100 5-speed end mills combine a 4-flute tool's versatility with the increased feed rates of a 5-flute tool, ensuring maximum efficiency. These end mills are tested under extreme conditions, achieving machining records of up to 1000 cc per minute. The combination of advanced geometry and coatings ensures high performance in aerospace, automotive, and precision engineering applications. The Accura 65EL from HEDELIUS is a high-performance milling machine designed for dynamic machining. Equipped with a pallet system, it allows for fully automated workpiece loading and unloading, optimizing production efficiency. The machine is capable of high feed and high-speed milling, with spindle speeds reaching up to 24,000 revolutions per minute and feed rates of up to 30 meters per minute. It features 5-axis simultaneous machining, enabling precise production of complex geometries with minimal setup time. The process begins with the workpiece being loaded onto the pallet, followed by automated machining programmed using SolidCAM. The use of 5-axis milling allows for intricate designs to be completed in a single operation, enhancing precision and reducing overall cycle time. After machining, the pallet system automatically unloads the finished part. This combination of high-speed performance, automation, and precise 5-axis control makes the Accura 65EL ideal for high-volume production with superior accuracy and efficiency. The high-tech 350 BYMC CNC lathe from Huaqian, Asia, specializes in hobbing and skiving operations. It handles workpieces up to 350 millimeters in diameter and 350 millimeters in length, with a spindle speed of 6,000 revolutions per minute and feed rates up to 10 meters per minute. The machine is equipped with a Siemens 828 DCNC control system, ensuring precise control. Automated loading and unloading processes enhance productivity, making it ideal for high-precision gear manufacturing. The piston production industry manufactures over 400 million pistons annually, primarily for the automotive sector. Precision is key, with tolerances often within plus or minus 0.005 millimeters. Advanced CNC machining and aluminum alloy casting dominate, supporting global engine manufacturing worth $250 billion yearly. Sheet metal stamping plays a vital role in manufacturing products like aluminum cookware and refrigerator evaporator panels. This process involves feeding aluminum or stainless steel coils, 0.6 millimeters to 2.5 millimeters thickness, into decoilers. After flattening, the material is cut into blanks, round for cookware, 240 millimeters to 320 millimeters diameter, and rectangular for evaporator panels, 300 millimeters to 600 millimeters long. Cookware blanks undergo deep drawing, with 2 to 5 stages, followed by edge trimming and surface treatments like anodizing. Evaporator panels are stamped, brazed at 600 to 620 degrees Celsius, pressure tested, and coated for durability. Automated lines ensure efficiency, with cycle times of 8 to 15 seconds per piece, while robotic arms enhance consistency and speed. Walter Hassenkamper Schrauben specializes in producing high-quality screws and nuts. The production process starts with material preparation, where steel wires or bars are cut to length, 20 millimeters to 200 millimeters. The blanks are then formed into the required shapes using stamping or pressing machines. Threads are created by either cutting or rolling, with common sizes like M6, M8, M10. The products undergo heat treatment for hardness, followed by surface finishing like zinc plating for corrosion resistance. Rigorous quality checks ensure dimensional accuracy and mechanical properties before packaging and distribution to clients worldwide. Fonderia Terroni, located in Italy, specializes in aluminum gravity casting, focusing on precision and high-quality production. The process begins with melting aluminum ingots in induction furnaces at temperatures ranging from 720 degrees Celsius to 750 degrees Celsius. The molten metal is then poured into steel molds, each capable of holding up to 10 kilograms of aluminum, with cycle times of about 5 to 10 minutes per casting. After cooling, the castings are moved to CNC machines for machining, where milling, turning, and drilling operations are carried out at speeds of up to 10,000 revolutions per minute. Tolerances of plus or minus 0.02 millimeters can be achieved on complex components. Following machining, the castings undergo heat treatment at 400 degrees Celsius for up to 4 hours to enhance strength and reduce residual stresses. Surface finishing is applied, with anodizing layers typically ranging from 15 to 25 microns to improve corrosion resistance. Finally, Quality control is ensured through 100% inspection, using X-ray machines and coordinate measuring machines, CMM, to check critical dimensions. This streamlined process guarantees high precision and reliability in aluminum castings for diverse industries. Stalcon specializes in the manufacturing and assembly of custom steel constructions, offering solutions for overhead cranes, pipe cranes, stacker/reclaimers, and more. They also produce tanks, silos, boilers, waste gas treatment installations, and shipping constructions like ferry ramps. Their expertise extends to industrial halls, trade pavilions, and sport facilities. Stalcon's team ensures high-quality production standards tailored to client needs across various sectors. The Torno Swiss Deco 36 TB is an advanced Swiss-type turning center designed for precision machining of complex parts. At the EMO Hanover 2019, this machine was showcased for its capability to produce intricate orthopedic components like intramedullary IM nails. It features a 36mm spindle with a maximum speed of 8,000 revolutions per minute and a torque of 53 Nm, ensuring efficient material removal. The Swiss Deco 36 TB is equipped with 3 Z-axes and a 12-position turret on a B-axis for complex milling operations. The machine excels in deep-hole drilling, capable of drilling up to 500 mm, ideal for applications like orthopedic trauma nails. A key feature is its high-pressure coolant system, with the option for 2 pumps, providing precise cutting fluid management. Additionally, the machine can connect to a cold water network or chiller, enhancing stability. The Swiss Deco 36 TB combines automation and precision, revolutionizing production in industries requiring high precision. Pickdockum produces cast iron using an efficient process. The process starts with melting pig iron and scrap metal in an 8-ton induction furnace at 1,300 degrees Celsius to 1,500 degrees Celsius, taking about 1.5 to 2 hours. The molten metal is alloyed with 2% silicon, 1% manganese, and 0.5% carbon. It is then poured into molds, typically 250 mm by 300 mm, and allowed to cool for 3 to 4 hours. After cooling, machining is done using CNC technology, with tolerances of plus or minus 0.1 mm. Quality control is performed through Rockwell hardness tests and X-ray inspection. The feed screw manufacturing process starts with a rough steel bar that undergoes several steps. First, it's turned on a lathe to precise dimensions. Then the bar is channeled using milling machines to create a spiral groove. Hard-facing alloys are applied to the screw's flights for durability. After welding, it undergoes slow cooling in a tank. The screw is then ground, polished, and chrome-plated for a smooth finish. Finally, drive components are added, completing the feed screw, which is now ready for industrial use. Navantia, CEFAN, a leading shipyard in Spain, uses 3D printing technology for manufacturing ship parts like rudders. The process begins with 3D CAD design, followed by preparing the data for 3D printing. A 3D printer then creates the rudder layer by layer, which can take from several hours to days depending on size and complexity. After printing, the rudder undergoes heat treatment to enhance strength, taking 4 to 8 hours. Quality checks like ultrasonic and X-ray testing ensure it meets strict standards. The final step is finishing and assembly, ensuring efficient and high-performance ship components. For professionals in the machining industry, understanding the power behind high-performance tools can make all the difference. This video takes you through the process of ISO turning, drilling, and tapping, with indexable inserts from Tool Factory Cutting Tool Solutions. These tools, crafted from solid carbide grades and coated with advanced technology, deliver unmatched material removal rates and exceptional tool life. The process begins with precision setup of the indexable inserts, ensuring efficiency and reliability across a variety of machining applications. Discover the detailed production process behind Fundicao Moreno's high-quality castings. The company has been a key player in producing cast steel and iron components. The process starts with the preparation of models for large-scale production, ensuring precision in every step. The foundry uses advanced techniques for molding, pouring, and heat treatment. After casting, the parts undergo deburring, machining, and pre-assembly to ensure every component meets strict quality standards. Advanced laboratory tests, including chemical composition and ultrasonic tests, ensure that each product is of the highest quality. This approach helps create parts like sugar mill rollers, designed to enhance productivity in the sugar and ethanol industry. The video takes us inside the aluminum casting process at GEASRL, beginning with the preparation of the aluminum alloy. This alloy undergoes purification to remove any impurities, ensuring high-quality results. The next crucial step is degassing, where sodium metal is added to remove air, preventing microporosity in the final product. The molten aluminum is carefully poured into molds, requiring precise timing and technique to achieve optimal casting quality. The company stresses the significance of recycling aluminum, contributing to sustainability. Only top quality, preferably Italian-made ingots are used, emphasizing the excellence associated with the Made in Italy label. The Anyang hot forging press machine is used for metal forming under heat and pressure. The C86Y75 model has a pressing force of 75 tons, 750 kilonewtons, and a ram stroke of 1250 millimeter. It operates with a 55 to 75 kilowatts motor and a hydraulic system that generates pressures up to 250 megapascals. Parts are made from high-strength steel, machined with 0.01 millimeters precision. The press runs at a rate of 55 to 70 strokes per minute. The total weight of the machine ranges from 5,000 kilograms to 15,000 kilograms depending on the model. It is subjected to rigorous quality control and testing before shipping. The D53K series ring rolling machine operates through a combination of radial and axial rolling processes to form seamless ring forgings with high precision and efficiency. The process begins by heating a pre-formed billet, typically made from carbon steel, alloy steel, or other metals, in an induction furnace to a temperature between 1,100 degrees Celsius and 1,250 degrees Celsius. Once the billet reaches forging temperature, it is positioned in the ring rolling machine between a central mandrel and a drive roll. During operation, the radial roll applies inward pressure on the outside diameter of the heated billet, while the mandrel expands the inner diameter, forming the initial ring shape. Simultaneously, axial rolls apply vertical pressure to control the height and thickness of the ring. This dual-axis rolling ensures uniform material flow, precise dimensional control, and structural integrity throughout the forging. The D53K machine utilizes hydraulic force, delivering up to 8,000 kilonewtons of pressing power. It accommodates ring diameters ranging from 350 millimeters to 8,000 millimeters and heights from 60 millimeters to 800 millimeters. Rolling speeds vary between 0.5 meters per second and 1.3 meters per second, depending on the material and desired ring size. The machine's operations are managed via a Siemens PLC system, which allows for automated control, real-time monitoring, and adaptive adjustments to optimize rolling parameters. Once the rolling process is complete, the forged ring is transferred for heat treatment processes such as quenching and tempering to enhance its mechanical properties. The ring may also undergo finishing steps like machining, grinding, and polishing to achieve the required surface and dimensional specifications. Rigorous quality inspections, including dimensional and hardness checks, ensure each ring meets the necessary performance standards for applications in aerospace, automotive, energy, and heavy industrial sectors. Forgewell Industries, located in Pune, India, has been a leader in the forging industry since 2010. The company is known for producing high-quality forged products using advanced techniques. The process begins with sourcing premium raw materials, which are then heated to the precise temperature required for forging. Once heated, the materials are shaped under high pressure with hammers or presses, resulting in strong, durable components. After forging, the products undergo a series of quality control tests to ensure they meet the stringent standards of various industries. Forgewell Industries is committed to providing reliable, high-strength products for various applications, making them a trusted partner in industries like automotive, aerospace, and construction. Vaughan Electric's motor rebuilding process begins with disassembly, where technicians carefully remove and inspect components. Next, parts undergo cleaning to eliminate contaminants before detailed inspection and testing detect faults. Damaged components are repaired or replaced, ensuring functionality. The motor is then reassembled with precise alignment. Finally, advanced testing evaluates performance, including high-voltage tests up to 4,160 volts and dynamometer analysis. The vacuum pressure impregnation (VPI) system enhances insulation, ensuring reliability and efficiency in the rebuilt motor. Expertise steps in. At CJ Plant, the restoration of a Komatsu PC 450-8 hydraulic pump begins with a thorough polishing. Each part is expertly ground and smoothed to remove any imperfections, ensuring optimal performance. After this, the pump components are thoroughly cleaned, removing any dust, oil, or residue left from the grinding process. Once clean, the damaged or worn-out parts are identified and replaced with genuine Komatsu components. The pump is then carefully reassembled, and its functionality is tested using compressed air to verify proper operation. This detailed process ensures the hydraulic pump is restored to peak performance. Every step in the rebuilding phase is executed with precision to guarantee the pump meets the highest standards. Additional checks are conducted throughout the process to ensure there are no hidden defects. The pump is also tested under varying pressure conditions to simulate real-world usage. Once the pump passes all tests, it undergoes a final inspection and is then shipped to our customer in Norway, backed by a 12-month written warranty. Oxygen lance, a heat-resistant pipe, is connected to an oxygen supply. The operator ignites the lance using an external heat source, such as an oxyacetylene torch, reaching temperatures over 2,500 degrees Celsius. Once ignited, the operator directs the oxygen stream onto the metal surface. The intense heat causes rapid oxidation, turning the metal into molten slag. The continuous oxygen flow blows the molten material away, ensuring a precise cut. This technique is widely used in steel mills, foundries, and demolition sites to cut through thick steel, remove excess material, or dismantle large structures. Operators must wear protective gear, including heat-resistant clothing, face shields, and gloves, due to extreme temperatures and molten metal splatter. Proper ventilation is crucial to disperse fumes and maintain safety. Compared to conventional cutting methods, oxygen lance cutting offers high efficiency, especially for thick or reinforced steel. However, it requires skilled handling to control the cutting depth and speed accurately. This process remains essential in heavy industries where conventional cutting methods may be inefficient or impractical. Four-die forging devices are high-performance mechanical systems used in metal forming to achieve precision, efficiency, and consistency in large-scale production. The process begins with the design and manufacturing of 4 interconnected dies, each responsible for a specific shaping stage. These dies are made from high-strength materials and precisely machined using CNC technology to ensure durability and accuracy. Once the dies are prepared, raw metal billets are cut to the required size and heated to optimal temperatures, increasing their malleability and reducing the force needed for deformation. The heated billet is then placed into the first die, where it undergoes sequential shaping through compressing, bending, stretching, or trimming in the subsequent dies. This step-by-step process ensures uniformity in the final product. After forging, excess material is trimmed, and the product may undergo heat treatment and surface finishing to enhance mechanical properties. Quality control is crucial, involving dimensional inspections, strength testing, and structural integrity checks to ensure high standards. The 4-die forging process significantly improves productivity, minimizes material waste, and enhances product reliability. Due to the high speed and high force operations involved, strict safety measures, including protective systems and operator training, are essential. This technology is widely used in heavy industries, automotive, and aerospace manufacturing. Kamaharitsu Kosho specializes in manufacturing cast steel components for ships and industrial equipment. The production process consists of several key stages. First, wooden patterns are crafted to create precise sand molds. These molds are then used in the sand molding stage, where compacted sand forms a negative shape of the desired part. Next, in metallurgy, scrap steel is melted in large electric furnaces. Skilled technicians adjust the chemical composition before pouring the molten metal into molds. After cooling, the hardened cast is removed and undergoes finishing processes, including grinding, welding, and machining, to achieve the required specifications. Finally, the components go through rigorous quality inspections, such as dimensional checks and non-destructive testing, ensuring high standards before shipment. This meticulous process blends traditional techniques with modern technology to produce durable, high-quality steel parts. The feeding process for the 75-inch tandem mill involves several steps. First, steel coils weighing 10 to 30 tons with a thickness of 6 to 12 millimeters are placed into the feeding system. The coils are aligned and guided into the mill, which consists of 4 to 6 sets of rollers. The mill reduces the steel thickness in stages, with speeds reaching up to 1,500 meters per minute. The final product is wound into coils, typically weighing 10 to 30 tons. HEMA provides advanced welding and production automation solutions tailored for heavy industries, such as shipbuilding, offshore, industrial boilers, mobile machinery, and wind energy. These systems are designed to streamline workflows, increase productivity, and maintain consistent quality even in large-scale production. The video showcases an array of PEMA's robotic and semi-automated solutions in action. One highlight is the robotized submerged arc welding system, which delivers deep, clean welds with minimal human intervention. These systems are ideal for heavy steel structures and massive workpieces, ensuring durability and precision. The automation systems also support various welding processes including MIG/MAG, TIG, and laser hybrid welding. The integration of robotic arms, advanced sensors, and CNC-controlled platforms allows precise control of weld paths, speeds, and positions. Workpieces are clamped and rotated automatically, enabling continuous, uninterrupted welding operations. The entire system is controlled via intuitive user interfaces, allowing operators to monitor key parameters in real time. Thanks to automatic seam tracking, adjustments are made dynamically during the weld process, reducing errors and ensuring consistent results. Data logging and remote diagnostics also support predictive maintenance and production tracking. The setup often includes custom handling systems and intelligent software, which reduces setup time and operator workload. In industries like offshore wind towers or pressure vessel production, the solutions drastically improve output without compromising quality. The modular approach enables scalable automation, from single welding stations to fully integrated production lines. By reducing manual labor and increasing repeatability, manufacturers can ensure safety, lower costs, and boost output. Their technologies represent the future of efficient, intelligent manufacturing in the welding industry. Discover the innovation behind U.S. Pipe Fabrication, the largest independent ductile iron pipe fabricator in the United States. Since 1991, U.S. Pipe has revolutionized the ductile iron pipe fabrication industry, providing high-quality fabricated products and excellent local service across the country. The fabrication process starts with the careful selection of premium raw materials, which are then molded and cast into pipe sections. These sections undergo a series of rigorous tests, including pressure tests, to confirm they meet the required performance standards. Following this, the pipes undergo heat treatment and are finally machined to achieve their final shape. Each pipe is thoroughly inspected for defects before being shipped. U.S. Pipe's state-of-the-art machinery and highly skilled workforce ensure that every pipe produced meets the highest industry standards, offering long-lasting and reliable solutions for various sectors. With 12 locations across the United States, U.S. Pipe maintains its position as the industry leader in ductile iron pipe fabrication, delivering unmatched products and exceptional service. The company's commitment to quality and innovation has made it the trusted choice for a wide range of industrial applications.